Hello, welcome to Chapter 13, Section 1, where we are going to introduce trigonometry involving right angle, or right triangles actually. It's called right angle trigonometry, as you can see. This is the first video in this section where we're going to introduce this idea. So I'll talk a little bit about it. I'll talk a little bit about the vocabulary, and we'll do some of the examples. For the first part, we're going to introduce these ratios called the sine, the cosine, and the tangent. So let me try to explain it this way, and you can read it all, you can pause it all, but I'm going to talk about it a little bit. We'll start off with this easy, the famous 3, 4, 5 right triangle. We know it's a famous right triangle because we usually use this as an example of the Pythagorean theorem. 3 squared is 9, 4 squared is 16, 5 squared is 25. 9 plus 16 equals 25. So if I look at this triangle right here, I can see that I've got 3 sides, and I can make 6 ratios, but here's the big 3. The other 3 are just the reciprocals of those. We'll talk about those in a later video. So I can choose to do 4 over 5, 3 over 5, or 4 over 3. I can also do the other, like I said, reciprocals, but like I said, hold on to that for just a little bit. Now, here's the thing about this. This angle right here, which we're going to give we use the Greek letter theta, the lowercase theta actually, as kind of like a variable for angles that we don't know. And we can figure this out for this one, okay? That'll come again. This is the hard part about this video. It's like there's so much of it like, yes, this is coming later. Think of it as like taking the place of an angle measurement that we don't know yet. All right, so think of it as kind of like an X. But just to distinguish it a little bit, to let us know we're actually looking for the measurement of an angle, oftentimes we use theta. And that's one of the things that is kind of like we all agree just to do that. So relative to where this angle is, I've got these 3 sides. Well, these 2 sides are called legs. All right, they're both called legs. So we have to distinguish which leg is which. This side is called the hypotenuse. The hypotenuse is always the longest side of a right triangle. The hypotenuse, well, let me explain it this way. The 2 legs make the right angle, and the hypotenuse is the other side. So we're going to introduce the idea of how to name these legs. And if I look at where this angle is, angle theta, I'm going to cover this up. Angle theta is made out of the hypotenuse and this leg. Well, the leg that makes the angle right here, we call it the adjacent side. Adjacent is a fancy word for saying next to. So adjacent to angle theta is this side, which in this triangle is measured 3. That leaves this other leg, and since that leg is not one of the sides that make up the angle, but it's across from the angle, here's the angle over here, here's the side over here, we call it the opposite. So the 3 sides that we have here, we give them kind of like nicknames. This is always the hypotenuse, that's a geometric term. But these 2 legs, this is the adjacent leg to the angle and the opposite leg to the angle. Now here's the tricky part, and I'm going to mention this, and we'll bring it up when it becomes relative, okay? But don't worry about it right now. If I'm actually looking at the other angle, the one up here, this one, then this side is opposite of that side, of that angle, excuse me, and this side is adjacent. So it's always, which side is opposite, which side is adjacent, is always relative to which angle you are talking about. So please be aware of the fact that we're always going to talk about which angle, and you have to use that angle to figure out which side is opposite, which side is adjacent. All right? So remember that. That also falls into like why we call this cosine. I'll talk about that in a second. Now, here's something that's kind of cool about well, similar triangles. And I'm not going to draw these to scale. I'm going to redraw this one. So let's say this is 3, 4, 5 again. And I know it doesn't You're going to have to pretend. I'll scoot that up so you can see it. If I have another triangle, and I'm not drawing this to scale or anything, but let's say this is 6, 8, 10. And of course, that's a 90-degree angle. Clean that up just a little bit. Now check this out. I know that 6 squared is 36, 8 squared is 64, and 10 to the second power is 100. 36 plus 64 equals 100. So I've got another right triangle, but also all I did was I scaled this up by 2. So I multiplied 3 times 2, 4 times 2, and 5 times 2. This is another triangle that is similar to that one. I actually have an infinite number of triangles that I can draw that are in this shape that are all just an infinite number of different sizes. I take my basic 3, 4, 5, and you'll make that look a little bit more like a 5. I take my basic 3, 4, 5, and I can multiply all the sides by any number, or I can even divide. I can have 1.5, 2, and 2.5 if I divided everything by 2. Why is that important? Because if I take, for example, here's my theta again, and these two are similar, so the angles are the same. So if this angle, I didn't give myself enough room, but if that angle's theta, then so is that angle. So, and because they are similar, there's a whole bunch of geometry here that I'm trying to squeeze into this video, all right? So if I said, all right, let's find out what the opposite over the hypotenuse is for theta, that's 4 over 5. But in this triangle, and again, these are the same angle measurements, the opposite over the hypotenuse is going to be 8 over 10. Well, it's easy to see that these two are actually equal to each other, because if I reduce 8 over 10 or simplify it, I get 4 over 5. You can cross multiply. 5 times 4 is, 5 times 8 is 40, and 4 times 10 is 40. So I know these fractions are equal. And also, if you wanted to, I suppose you could change them to decimals. 0.8 equals 0.8. What happens is, when I scaled this one up by multiplying 3 times 2, 4 times 2, 5 times 2, that 2 is what I reduce by here, by that scale factor. It goes back to the simplified form. So what does that mean? That means that as long as I have a triangle that is similar to a 3, 4, 5, which is any scaling of it, the ratios opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent are all going to simplify and be the same. It's going to be constant. Those are the trigonometric functions. So we define it this way. And these are the names: sine, cosine, tangent. It's spelled that way. The abbreviations: sine is S-I-N, cosine is C-O-S, and tangent is T-A-N. You'll see these on your calculator, and unfortunately mine's out of reach right now, so I should have planned for that. But that's okay. You can look at your own calculator. I'll show it in one of the later videos. Actually, probably the indicator whether or not you have what we call a scientific calculator is I tell students to look for the sine, cosine, and tangent functions on your calculator. So what are sine, cosine, tangent? Well, here they are. The sine is the ratio of the opposite side over the hypotenuse. Opposite over hypotenuse. And that's constant for whatever angle you're going to pick. So the sine of 30 degrees, if theta was 30 degrees, is constant, no matter how big the triangle is. The cosine is the ratio of the adjacent side over the hypotenuse, and the tangent is the ratio of the opposite side over the adjacent side. Now there are 3 other trig functions, and like I said, this comes up actually in the last example. All they are the reciprocals of what we have. So we have a trig function that is, instead of sine being opposite over hypotenuse, we do hypotenuse over opposite. And then same thing, instead of adjacent over hypotenuse, we have hypotenuse over adjacent. And instead of opposite over adjacent, we have adjacent over opposite. We'll bring that up in, I think, example 4 or example 5. So we'll see those a little bit later. Usually these are the 3 that take care of what we need. And that's why you only see those 3 on your calculator. To get the other 3, you just find the reciprocal of them. Okay, So let's do a couple of examples. That's a lot of information, but let's do a couple of examples and maybe this will help clear it up a little bit. All right. So I have this triangle. And again, this triangle is a right triangle. You can use the Pythagorean theorem to figure these out. 36 squared plus 15 squared plus 39, equals 39 squared. Pause the video and do that with your calculator if you want to. What I want to do is I want to find the trig functions for this angle theta. I don't know what the angle is. That'll come up later. I know I keep saying that, don't I? But I want to find out what the trig relationships are for this triangle. Okay, so I know that sine of theta is going to be the opposite, and I'm just abbreviating OPP for opposite and HYP for hypotenuse. And the cosine of theta is going to be the adjacent. I'll use ADJ, and again, that's usually what we do, over hypotenuse. And the tangent of theta is going to be the opposite side over the adjacent side. Now, I want to just mention one thing real quick. If you go back and see what I stole from the book, they don't put parentheses around the input of these functions. Sine, tangent, cosine, and the other three are trigonometric functions. As a matter of fact, that's the title of the chapter. In order to make a function work, you have to put the input inside parentheses. And this is one of the things that drives me crazy, because I've done this enough and I know what it is, I recognize it, but for someone who's learning algebra, learning this for the first time, it's like, why are we changing the rules? So when I do it, unless I get sloppy, when I do it, I'm going to put this in parentheses, kind of like f of x, using parentheses. And if you've been following along, you remember that I had the same discussion when we were talking about logarithms, because a lot of times we don't properly use parentheses for logarithms. Okay, so just put that aside. So let's look at this triangle. Here's my angle theta. This side is opposite, actually, there's that opposite of the right angle. These two legs make up the right angle, so this third side, that's going to be the hypotenuse. And again, the hypotenuse is always opposite of the right angle. It's not opposite of theta, okay? Rewind that and listen to what I said again. But it's opposite of the right angle. Opposite of theta is over here, which is measured 15. That means that this side, which these two sides right here make up angle theta, this is going to be the adjacent side. Okay, so now I want to find opposite and make it into a ratio with the hypotenuse. The opposite side is 15, the hypotenuse is 39. So the ratio is going to be 15 over 39. That's great. The only thing I have to do now is check to see if I can simplify by reducing. It looks like both of these, I'll clean that up a little bit, both of these are multiples of 3. So 15, if I factor out a 3, 15 is 5 times 3, and 39 is 13 times 3. So this is going to reduce to 5 over 13. Let's try adjacent over hypotenuse for the cosine. The adjacent side is 36, and the hypotenuse still is 39. And again, this looks like I can simplify. Both of these again are multiples of 3. So this is 12 times 3, and this is still 13 times 3. So this reduces to 12 over 13. And finally, for the tangent, the opposite is still 15. The adjacent is still 36. So that's 15 over 36. As they have been, these are still multiples of 3, so I can reduce and get 5 over 12. Now this reducing part, this actually comes from the fact that, just like I talked about here, I can take a famous Pythagorean triplet and scale it up. This is actually scaled up from another famous Pythagorean triplet. This is a 5, 12, 13. So 5 squared plus 12 squared equals 13 squared. And that's probably one of the Pythagorean triplets probably the second Pythagorean triplet that most people are introduced to. All right, let's do another example, and then I'll wrap that up with this video. I know this one's getting kind of long because of all the introduction stuff. So here's my angle theta. Now notice that unlike last time, my angle theta was down here on the left at the bottom. That doesn't matter. If I turned it like that, then angle theta is up here, but all of the ratios are still the same. This is still the side opposite of angle theta. This is still the hypotenuse. This is still the adjacent side. If I turn it upside down, or if I rotate it any way I want. So the orientation doesn't matter. What you have to do is figure out which side is opposite and which side is adjacent relative to angle theta. So what do we know? In my triangle, this longest side is always going to be the hypotenuse. Here's angle theta. The sides that make up angle theta are going to be the hypotenuse and the adjacent side. And opposite of angle theta, the side that does not make up angle theta, I have to walk across the triangle to get to it, this is going to be the opposite. So sine of theta is still going to be opposite over hypotenuse. Cosine of theta is always going to be adjacent over hypotenuse. And tangent, time to get a new marker, tangent of theta is always going to be opposite over adjacent. So let's look at sine. Opposite to angle theta, opposite is right here. So that's going to be 30, and the hypotenuse is 34. That looks like I can simplify this ratio by reducing it. 30 is 15 times 2, and 34 is 17 times 2. So I get 15 over 17. Cosine is adjacent over hypotenuse. Adjacent to theta is 16, and the hypotenuse is still 34. And that's going to reduce to 8/17. Finally, tangent is opposite over adjacent. So opposite is 30, adjacent is 16. And that's going to reduce to 15 over 8. And by the way, you can leave that. You don't have to change it to a mixed number. As a matter of fact, it's better if you don't. Just leave it as an improper fraction. And I hate that we call them improper. That's bad. Okay, we will be doing this more in the next couple of videos. We'll be seeing more about this. There's just one thing I want to wrap this up with. I'll go back to this one. The way that we remember this, it becomes kind of a mnemonic. And actually, it's kind of become the nickname for like basic trigonometry, all right? So you'll hear us say, okay, we're going to do this. We take the first letter to remind of what we have. So sine is opposite over hypotenuse, so we write S-O-H. Sine is opposite over hypotenuse. Cosine is the adjacent over hypotenuse. Cosine is the adjacent over the hypotenuse. And tangent is opposite over adjacent. Tangent is opposite over adjacent. So what you'll hear math teachers say is, remember SOHCAHTOA. You know, it kind of like makes a goofy word, all right? So it's actually an acronym, but like PERMDAS. But we use that a lot when we talk about just starting out with like basic trigonometry. So for all the problems we're going to be doing, whenever we want to find the sine, cosine, or tangent of something, we just say, okay, we're going to find SOHCAHTOA. All right? We'll see you in the next video.